Oh, hi, and welcome to another power electronics class. In the previous class, we went through some fundamentals of power electronics, some applications of power electronics. Today, we're going to continue with those applications, dive a little deeper into some applications of power electronics as well. And if we have enough time, start with some circuitry of power electronics and different components of power electronics. So one thing that power electronic gives us is control over voltage, current, frequency, and that gives us power, a very powerful tool to use it in a lot of applications. Some other applications of power electronics is in home appliances, refrigerators, washing machines, garage openers, vacuum cleaners, these cordless vacuum cleaners as well, and RF amplifiers and so on. One example that I see a lot in the past few years, all these refrigerators have switched to, is the compressor. Nowadays, they are using DC compressors. And the reason that they are using DC compressors, some of them, and they are using an AC compressor, but with an inverter, is because they would have control over the compressor. The problem with normal compressors was that you could either turn it on or off. So it was turned on or shut off. And when you do that, you're going to waste a lot of energy in the process. But when you use an inverter or a DC, you can have a precise control over the motor RPM and the torque. So instead of running 0 and 100% all the time, you can smoothly, very smoothly go from 0% to 100%. So you can, if the temperature is not that high, you can run it at 20% or 30% or 50%. And again, running on and off creates a lot of stress on the motor and also consumes a lot of power, wastes actually a lot of power. Again, these cordless drivers and these vacuum cleaners like the Dyson ones, nowadays all of them almost, especially the cordless ones, they use a brushless DC, what we call the BLDC motor. The BLDC is a type of DC which actually the principle works very similar to an AC motor, and I'll explain more about that. And those motors mainly use power electronics to control the speed and the torque of a motor. Some electric power systems that we have for the electric power quality, the power factor correction. As you remember, power factor correction, we have leading and we have lagging powers, and we usually use a capacitor bank for power factor correction. And measuring the power factor and so on, it has a lot of power electronic components to it. VAR, or volt amp reactive compensation, which is technically a type of power factor corrector. Flexible AC transmission systems, or what we call FACTS, and I'll explain more about that. High voltage DC or HVDC, and harmonic reduction. And then in the recent years, there has been a lot of use, and actually because of the advancement in IGBTs and power electronics, has gained a lot of attraction in EV, electric vehicles. So electric and hybrid vehicles in different parts, battery control management system, and what we call BMC, battery management system, which could control every individual cell battery voltage. It could control the charge level. And when something goes wrong, it will cut the power. It's a computer just dedicated to the battery to manage and extend the life of the battery. Another part in the EV that the power electronics is used is usually the EVs, then older generations, like the early Teslas, they use the permanent magnet DC motor. Now most of them are using AC motors, but with an inverter. So the inverter is a power electronic, and I would explain more about the inverters. It's a big part of this course. ABS or anti-lock braking systems. The steer-by-wire, now 2 cars have it. The Tesla Cybertruck, they use it, steer-by-wire. Some models of Lexus RZ also do have it as well. The ones that have a yoke, usually they are using that. I think it's going to be getting more and more prevalent in the auto industry. And brake-by-wire, starter, alternator, or air conditioning systems, and electronic ignition systems as well. And another application is in aerospace, aircraft and spacecraft power system, international space stations. Again, fly-by-wire, what they call it. All the controls are now through older generation airplanes. They use hydraulic systems. Now they use fly-by-wire. And electronic and power electronic is a big part of that. Telecommunications, wireless communication power supplies, uninterruptible power supplies, or what we call UPS systems, and transportation, train and locomotive, EVs, maglevs, and most recently they are using these hyperloops. Use a lot of power electronic components. Commercial, like electronic ballasts, light dimmers, hand power tools, all of these, DeWalt and Hita you see right now, they are using BLDC. And controlling the torque and controlling the RPM requires a control system, a power electronic system. Battery chargers, electric fans, and so on. We have for medical, like these medical fitness devices, MRI, CTs, all of them, especially MRI. They consume a lot of power because they have to generate a very, very high magnetic field. It starts around 0.7 Tesla up to 10, 11 Teslas for what we call an fMRI machine, functional MRI. And those could actually even measure the brain activity, just not map the physiological part of the brain, but actually they are now used. They put patients in an fMRI machine, show them some videos, and they map their brain activities. So they require a lot of very high levels of magnetic fields, which has been possible with power electronics. Industrials like machine tools, pumps, timers, elevators, induction heating, compressors, press machines, circuit breakers, these modern automation systems, all these robotic arms and robotic systems, servo motors, most of them are controlled with power electronic systems, step motors, servo motors, and so on. And other applications like data centers, converters for integrated circuits, fuel cells, adjustable speed drivers, industrial automation system, robotics, and so on. Now, this is an example of what and how we used to control the flow rate of a water pump before the advancements in power electronics and what we do right now. This is very similar to the compressor example that I mentioned. So 10, 20 years ago, when they wanted to control the water flow in a water pump, we simply had a line input. And on that line input, we used a switch, which actually it was a contactor. And imagine that we wanted to control the water pressure. You had this water pump. Imagine you had a water pump in the well, and you wanted to use the water hose to, water your garden, okay, or fill up your pool. And you would have a switch, and you would turn on the pump, and the pump could run at 0 or 100%. Okay, so it's turned on and off. An AC motor usually was used, and the problem with an AC motor is that you can rather turn it on or off when you connect it to a outlet or the grid. And the only way that you could control the flow of water is to use a throttling valve. You just use the valve. And for example, if you just wanted the water at 10%, you would close this by 90%, and 10% of the water would go out. And what happened to the other 90% power of this AC motor? It's going to be wasted. And you're going to put a lot of pressure on the motor, on the pump itself. And it's going to heat up. It's going to reduce the lifespan of the motor. And you're going to waste 90% of the power. It's only efficient when you want to work at 100%, just, watering a field or something, a center pivot system that you want to water a cornfield, because you want to just turn it on and off. Those applications pretty simple, you just want to do. But if you want to have control of the flow of the water, this was very inefficient. So nowadays what we do, we use an adjustable speed driver. So the same line goes into the input line, goes to a adjustable speed driver and the motor, and that motor has the capability of running between 0 and 100%, but you can run it, for example, at 10%, 20%, and whatever you want, 50%, 100%. Now, how does this do it? How many of you have power systems? How many of you are familiar with AC motors? A little bit. Okay, good. So let's say you have a DC motor. Let's start with the DC motor, which is the easier one. How do you control the speed of a DC motor? The round revolutions per minute, RPM. So for a DC motor, if you want to control the revolutions per minute, you would control the input voltage, okay? So imagine you have a motor which is connected to a battery, and that's itself creates a lot of problems, and I'll explain why. And this is adjustable voltage supply, and you can move between, let's say, 0 and 12 volts. So if you put it at 6 volts, this would run at 50% speed. If you put it at 12 volts, it's going to run at 100%. And if you put 0, obviously it's turned off, okay? So you can control the speed, rotational speed of a DC motor, permanent DC motor, by changing its input voltage. But now, how can I change? There's another question. How can I change the input voltage? How can I? So imagine DC motors mainly work on a DC power supply, which is a battery. How, in this particular case, I have a motor. Imagine I give you a AA battery. I want you to run a small DC motor. I wish I had one. I brought it with me. I forgot. And you want to just control the speed, rotational speed. How can I do that? What other component I can add to be able to precisely control the voltage that goes into the motor? Perfect. One option that I could use is I could just use a variable resistor, and the variable resistor could be connected to the motor, and by controlling this R, if the resistor goes up, what happens to the voltage? Drops. And if the resistor goes down, what happens to the voltage? It goes up. So adding a variable resistor, I can precisely control the motor. And we use it for small motors, and I'll explain why don't we use it at all for large motors and so on, and when we need high efficiency, because everything that is not consumed by the motor, it will be consumed by the resistor. Okay, so if I drop the voltage by 50%, 50% is consumed by the motor, 50% is consumed by the resistor. You remember we had the voltage divider. Okay, the larger the resistor is, it's going to consume more, it will have a higher voltage compared to the smaller. So now imagine that we want to run this motor for on 10% for half an hour, then 90% of the voltage would be on the resistor. And if it's not a good resistor, it's going to melt down the resistor. So that's one problem. You need to have a heat sink. It's going to be very difficult if it's a high voltage. And the other problem is you're wasting 90% of the power of the battery. And when you're using a power, that's a big deal. So instead of the battery running for 10 hours, it's just going to run for 1 hour. So we're going to use a power electronics. I'll explain what type of power electronics we use. The main point that I wanted to say for this part is that when you want to control a DC motor, you can control the speed of it by controlling the input voltage. Okay. Now, for a DC motor, as I mentioned, the input voltage controls the speed. What about an AC motor? Asynchronous AC motor. There are a couple of ways, especially for asynchronous as well. But I'm just speaking with a squirrel cage or inductive motor and an inductive AC motor. So for DC, you control Vn. What about AC? How can I control the rotational speed of an AC motor? Did you have the equation 120 N over P is equal to F? The rotational speed. So the rotational speed of an AC motor depends on two main things. One is the number of poles when you have an AC synchronous motor. And again, you don't have any control over the rotor's current, or on the frequency. Okay, obviously you can't change the number of poles in an AC motor because that's when you build it, it has 2 poles, 4 poles, and so on. But what you can change is the frequency, the input frequency. The higher the input frequency is, the higher the RPM would be. Okay. So by changing the input frequency, you can change the input RPM of a motor. Okay. Now, how can I change the frequency? So the equation is actually this. This is good for you to know. So RPM would be equal to 120 times the frequency F over the number of poles. We show it with P. And let's solve a practice problem. This is a good practice problem. I think you already have this power systems, but I'm just going to do a practice problem on this as well. So imagine we have a good example is the coal power plant, Exo power plant. Have any of you worked in Exo, been to the coal power plant? Yeah, good. So you see that they have I think it's 300 megawatts of power plants when we went there. Let me ask this question. What are our outlet voltages and frequencies in the US? Yes, it's 120 at 60 hertz, okay? The voltage is obviously determined by the transformers and the transmissions, but for the generator to create or produce 60 hertz, if that generator that is in Exo power plant, if we have 4 poles, if the generator has 4 poles, at what RPM should the generator spin to create 60 hertz? So the turbine, at what frequency should that spin? So the generator will spin and create, and as you know, you have a turbine, and that one is a gas power plant. I'm sorry, heat power plant, and it's a coil. They wanted to convert to gas. I don't know if they have done it yet or not. They were in the process, yeah. So they have a boiler that they heated with coil, and the steam goes into the, you know, the turbine, and it runs the generator, okay? Now the generator creates, let's say, a 500 volt, something like that, but the frequency is important to us, 60 hertz. Now, what is the RPM? At what speed should this rotate and this rotate to create a 60 hertz? Perfect, yes. So the RPM would be 120 times 60, which is divided by 4. So this and this creates 3. So RPM would be 1800. If it had 2 poles, then it would be, what would it be? It will be 3600, okay? So the lower the number of poles, it must spin faster, and we have limitations for that. Now, how do they control the rotational speed? They have a valve over here, and by controlling the valve, the amount of steam coming in, they could actually determine the frequency. And depends on the load and everything, they have a, you know, sophisticated algorithm to determine when the load is peaking. They don't want to let the frequency drop. When the load peaks, you have a drop in the frequency. So usually at early evenings, they will ramp it up, and they have specific, you know, I don't know how many of you work in Excel, but you may be familiar with some of these. Now, this is how we determine the RPM, okay? This is for a generator. For a generator, we can control the input valve and control the rotational speed. But what about a motor? If we have a motor and we wanted to, let me write, I'm sorry. Let me write the equation again here. So RPM for an AC motor is 120 F over P. P is the number of poles. And we usually use show this with N as well. N as RPM. Now, for an AC motor to control the rotational speed and therefore the amount of water we pump in this particular case, we need to control its frequency. Now, to do that, we use a type of inverter, and what we do is basically we convert AC to DC, and then we convert DC back with an inverter to AC. So we use a rectifier to convert AC to DC, and when we have a DC voltage, we use another inverter to be able to convert DC back to AC. But the second inverter, we would have a variable frequency. We can control the frequency very, very precisely. And say if, for example, let's do this exercise, and the RPM is the same for the motor as well. Imagine this has 8 poles or 6 poles. Let's say it has, I think 4. Let's say it has 4 poles. So P is 4. And we wanted to run at RPM. I wanted to run at, let's say, 6,000 RPM. what would F be? And this is when the motor is running at, let's say, 80%. So when the motor is running at 80%, the number of poles is 4. The RPM is 6,000. What is our frequency? You got what? 200. Okay. So let's solve this. So the RPM, again, using that equation, I don't want to rewrite the equation. I don't have enough space. So 6,000 would be equal to 120 times F over 4. 30. So F would be equal to 6,000 over 30. So 6,000 over 30, it's going to be 200. Now, what if I want this to run at, let's say, 2,000 RPM? What if I wanted to run at 2,000 RPM? What would F be? So 2,000 divided by 30, it's going to be 66.6, yes, hertz. So you can see by lowering the frequency, you can lower the rotational speed. And in this particular case, you obviously have some, drops in the efficiency, but the good thing is you can precisely control the motor speed. And the other problem that we have, you may ask, why don't we just simply switch to a DC motor? DC motors are expensive. They require permanent magnets, rare earth materials, and they're expensive. AC motors are very simple, easy to produce, and usually the lifespan is higher when it doesn't require maintenance because it doesn't have, commutators, and it's much more easy. It's much easier to maintain and produce. So sometimes it's easier to build a AC to AC, adjustable speed drive and converter than just use a DC and so the DC, you need a controller for that. So conventional drive wastes energy across the throttling valve to adjust the flow rate. Using power electronics, motor pump speed is adjusted efficiently to drive the required flow rate without the loss. Another example is a switch mode power supply. So on the right, we see an old school traditional power supply. And on the left, you see a switch mode power supply. And I remember the ones on the right, the earlier generation of power supplies, chargers on the phone, they were bulky, big. I don't know if you had one of those phones that, before these smartphones even, had bulky chargers. And also the laptops, the chargers were, now they are using IGBTs and, power electronics. They are making the chargers smaller and smaller. And on the left, you have a switch mode power supply. Now, how does it work? So for a normal power supply, if you had a normal AC to DC, if you want to use a DC power supply to charge your phone, and those who had electronics with me, you remember in the lab, one lab that you did actually for your final project was to build a AC to DC, a rectifier with a power supply. So how did we do it then? So a normal AC to DC, you have a transformer, and you would convert the 120 volt to 12 volts. And after that, you would run that transformer through a bridge rectifier. And the bridge rectifier is then connected to a series of capacitors and resistors, and finally you have the output V out. Okay, so you are converting the AC signal to DC. First you are stepping down the voltage, then you're converting AC to DC, and finally what you do is you would smooth out the signal. So the input signal will look like this. When it passes the 12 volts, it's going to look like this. Let me make this. So the input is 120 volts. Then it goes to 12 volts. Then when it passes the bridge rectifier, what happens to it? It becomes like this. And finally, when you pass the capacitor, I'm going to draw it with green. It's going to smooth out the ripples. And finally, you're going to have something that looks like this, very close to a DC. Yes? Okay. So the problem with this, there is a more clever way to do this. Instead of going through all of these and reducing the voltage here, and one thing that I have to mention, the bulkiest part of a transformer or a power supply is the transformer itself, okay? Because the transformer, you can't make it too small. You need a certain amount of primary coil turns and secondary turns. In this case, it's 10 to 1 because you want to reduce it 10 times, okay? But there is an easier way to do that. What if, and we know that this is a full wave rectifier, but when I have a half wave rectifier, do you remember if I had one diode, I would cut off half of the power and I will keep one half, okay? So I would get rid of the negative part and I would just keep the positive part of the. Now my average power is around 50%. Actually, it's less than 50%, 40%. So immediately I cut the power in half. So instead of having a transformer that reduces the voltage 10 times, I can have a transformer that reduces the voltage 5 times because I'm going to get the same results in the output. So what I can do is I can put a diode at the beginning. Okay, so this is a good example. And what it does, it's at the beginning, it just goes from this to this. Okay, so now I've reduced my output power by 50%. Now I would need a transformer, which is half the size of when I didn't have that transformer. And the component's getting much smaller. You can build it very, very, very small. And actually, this is the exact same thing that happens in your hair dryer. And I've opened a couple of them. I usually, when I buy something, I open it. I don't know. But the thing is, and my wife gets very mad, but I open it, I just want to see what's inside. And some of these cheaper hair dryers, when they have two levels, they have a low and high, setting. And when you put it at high setting, the power goes directly to the fan and also to the heater, which is a coil heater. But when you put it on in low, it actually goes through and it's a very simple but clever idea. When you put it on high, the outlet is connected directly to the fan. This is the fan and the heater, which is a coil. But when you put it on low, you actually connect it to a diode. And what that diode is just sends 50% of the power. So without the diode, the whole power goes through the heater. You would have maximum heat. But when you put it on the low, you have half of it. But some of them also have a coil that cuts off this heater. Some of them have low, medium, high. That's different. But most of them just have low and high, the cheaper ones. And they just When you connect it to low, it's like this. When you put it on high, the switch is connected to the one here, and when you put it on low, it's connected to here. So high and low. Okay, so these two switches, you can switch from the diode or without the diode. So the transistor is operated in switch mode, either fully on or fully off at high switching frequency. Electrical isolation achieved by high frequency transformer, smaller, lighter, and more efficient, and the results would be a compact and efficient power supply. So in more advanced cases, instead of this diode, we use a transistor, and the transistor, because in a diode, we don't have any control on when it's turned on and off. It's with the input. But I can make it more advanced and replace that with a transformer. I'm sorry, with the transistor. Instead of it being on 50% of the time, I can make it on 25% of the time. So it's going to look like this. At 25%, at only this portion, it could be turned on. Okay. So 25, 10, 5%, I can do it with a transistor, and that actually makes the transformer even smaller, since you can build a transformer which is 10 times smaller than the original one that you need to put. Now let's see how an AC motor drive, I already explained a little bit about this, how an AC motor drive works. But as mentioned, an AC motor drive is a device that is able to precisely control the RPM, the rotational speed of an AC motor. And the way that an AC motor drive works, it converts AC to DC and then converts DC back to AC. So we have two converters. I'm going to call it C1 and C2. C1 converts AC to DC. Okay, and we have this capacitor to smooth out any ripples and so on. So C1 is actually a rectifier. And then we go from DC to AC again, which is an inverter. So converter 1 rectifies line frequency AC to DC. The capacitor acts as a filter, stores energy, and decouples the two converters. And converter number 2 inverts DC to variable frequency AC as needed by the motor. So for example, I can connect this to a utility with 120 volts and 60 hertz, and I can go to 120 volts, 20 hertz, for example, in the output, or 120 hertz in the output, or 2000 hertz in the output. So depending what, 2000 is very high, but around a couple hundred. Depends on how fast I want the motor to spin. This is an example of a pure electric or EV and a hybrid electric vehicle and the power electronic components of it. We have the engine generator, we have the main, parts, electric drive unit, the charge point, and the lithium-ion battery. In EVs, it gets sometimes very complicated because the motors also act as a generator. So when you put the brake on, it uses a system called KERS. It's kinetic energy reserve system, I think. Yeah, kinetic energy restoring system or reserve system. When you put on the brakes, what it does, it converts that mechanical energy, kinetic energy back to electrical and juices up the batteries. And these are some parts. We have the ECU, the HV-ECU, the input-output voltage wave control. There's a lot of controls because how fast you want to go. When you put on the brake, do you just use the generator and using the braking power of the motor, or you press too hard on the brake and the brakes come in actually? So there's a lot of processing. I think it's like 500 processing per second, something like that. It's very fast processing. And you have waveform and voltage boost control block diagram that shows how fast the motor should go. Should it work in the generation mode or generator mode or the electric motor and so on.
Does it use like magnetic field to charge the battery?
Yes, that's exactly. That's a great point and a great question. Yes, when you cut off the power, when you push the, so I don't know if you drove a hybrid or electric, the brakes feel a little spongy because the first like 10% when you push the brakes immediately cuts the power, and when it cuts the power, the wheels are still spinning, and when the motor is still spinning, now it acts like a generator. But now there is a control system that tells the battery that now you need to charge. So it's like a diode thing, and yes, that uses the rotational speed. It acts like a flywheel. Now it uses a magnetic field to create the electrical power and charge the batteries as well. So an AC could work both in generation and it's the same with the DC as well, and a motor mode. And yes, that's exactly what happens. And in a hybrid vehicle, it's a little bit more challenging as well because sometimes you have to cut off the engine as well because you don't want the engine to run at the same time as, so you have a clutch system that it gets very, very complicated in HV in a hybrid. So this is a waveform and voltage diagram. It has a torque sensor, you have a torque request, and then you have a position information, the waveform, the voltage, it measures the voltage, turn on the motor, then you have a current sensor, you have a rotational sensor, and so on. So some of them have 10 different ECUs for the hybrid motor, one for the IC engine, one for the motor, one for the battery, one for on the wheels, the speed sensors, and so on. So, and one other example in the power electronics is renewable power generation, PV. If you're interested, you can do for your senior design project. I can help you with one of these projects, like an EV golf cart. One team built a golf cart. I think it's still here. You can still work on it, and the renewable power generation. This is an example of PV inverter. Do you know what PV stands for? Photovoltaic. So solar panels, photovoltaic inverters, photovoltaic or solar panels, they only generate DC power. It's like a diode. It's actually like an LED. And then DC, you have to convert that back to AC. So you need a DC to AC inverter. You want to deliver maximum energy from a solar panel, so you need to have the controls over that and track this maximum power point as it charges with illumination and temperature. When the temperature goes up, it's true that at the middle of the day you create the most power from PVs, but the problem is that the middle of the day it gets very hot, and when they get hot, it's a semiconductor. If it gets too hot, you're gonna the efficiency is gonna go down. Resistance is going to go up. So this is a PV system at UNH, and this is a system that actually stores power as well. How does it store power? Using a water tank, a hydro pump, a hydroelectric pump. During the day, you can charge the battery, and also we can have 2 water tanks at different elevations. The excess power, you can pump water, store it at the upper level tank. At night, when you don't have solar power, you can just release that water through a generator and create electric power. This is not very efficient. The efficiency is around like 60-70% max, but it's very cheap. Especially if you're on a foothill or you have an elevation, you can easily, cheaply, generate power. And this is actually the main method they are using. Hydro storage system is the main method of storing power in the US. I think it's like 80% of it we are using hydro storage. You can use a dam and pump the water back into the reservoir, something like that. And also in the wind turbines, now newer generation wind turbines, they are using actually DC generators, some of them, because the most expensive component of a wind turbine is its gearbox right now and the motor, both of them. And the gearbox is like 50-60% of the entire weight sometimes. To reduce the generator and let's reduce the transmission, we need to switch from an AC generator to a DC, permanent magnet. Those are a little bit burgier, but they require a very small transmission compared to an AC, the one that we use in an AC. And the way that we have to do that, we have to have a lot of power electronic components, and we generate power in DC. And again, we have to convert that using an inverter to a AC, and that requires a lot of power electronics. So new generation wind turbines, they use DC generators to reduce costs, make it lighter, but on the other hand, you have to have a inverter. This is an example of a permanent magnet synchronous generator for wind turbines. I've added this from another class that I taught wind turbines. And you can see that newer generation wind turbines, instead of having the big bulky transmission, they just use a synchronous generator. And they convert the AC to DC, and again, DC back to AC. So instead of having a permanent magnet, this time we use an AC, but you have to convert AC to DC and DC back again. So extra step. Why do we even need to go through all of this? Because as you know, wind speeds are variable, okay? If, for example, the wind is blowing at 40 miles per hour, the generator is spinning at 1800 RPM. And if I just connect it directly to an AC motor, the output frequency, let's say it would be 60 hertz. Let's assume that that's not another happens. But if the wind suddenly goes at 80 miles per hour, and it's not linear, this is just for this equation, then the motor would spin at 3600 RPM. Then I would have a frequency of 120 hertz, okay? And that's going to cause problems. It's going to damage the whole grid. You can't even connect this to a transmission system. So you need to have a precise control. And that's one of the problems that we have with wind. You know, sometimes it spins slower and faster, and you have to always match the frequency from the generator to the grid. Okay. If it's higher, lower, it's going to damage the system. If it's lower, sometimes you would actually get power from the grid. It's going to act like a motor. If it's underpowered, it's on the frequency. It's going to act like more. In some cases, not all of this. Obviously, the industrial ones doesn't happen, but small. If you have a small wind turbine.
So is there like a power drop off when you're transferring it from AC to DC back?
Yes, yes, that's a great question. Yes, there's around 60-70% just goes through. Very good ones just make it 80 to 90%. Top of the, but
That's
you
just because of like the transfer of, so like if the RPM does go up, you're just trying to match that frequency. And
Yes.
Because that's the power drop off.
Yes. So what you do is technically when it goes up, it's like, great question. The frequency stays stable, but the current and voltage change. Okay, so you're gonna put more power into the system, but you're gonna keep the frequency. You know, so the power goes up and down, yes. And sometimes when the power goes way up, it's not like that's perfect question. Okay, great question. And I recommend that you take wind class if you're very interested in this. So what happens is we have a lot of different tools to be able to match that voltage and current. If the frequency is steady always, but if the wind blows too fast, we change the pitch and the yaw of the blade. I don't know if you pass a wind turbine in a windy day and you see it's just still, it doesn't move, because now the grid, we are producing too much power and we have to shut down the turbine. How would you do that? The blades actually move and you put it like perpendicular to the wind and it stops moving, or you can reduce the speed, okay? Sometimes you can increase the speed, so you move the pitch and the yaw. You can make it perpendicular, both the wind turbine itself and the blade itself. Both of them move, okay? And you can change the direction and the pitch yaw to move change the RPM of the hub and the blades itself. But the thing is, you can control that to a certain point. When the wind is blowing too fast and you're at 2 a.m. and no one is using the power, you have to shut that down. It's a waste of, because you already put a CapEx and OpEx, capital expenditures. You put a wind turbine and you're not using it. It's turned off 60% of the time. That's the problem that California right now has with the solar. They're producing too much in the afternoons. Like 80% of them are just turned off. You don't need that much power. But when you need it, you don't have enough of it. So that's a little bit of challenge with the renewables. But yes, you can control this by controlling the yaw and the pitch as well to, control how much power you're putting into it.
When we're producing too much, that mostly because of how faulty our power grid is, or is it more kind of just?
No, it's a whole, generation power. Some power generators are on all 24/7. Like nuclear power plants, you can't turn them on. It may run for 2-3 years before you have maintenance or want to change the core fuel. Or the coal power plants, they run at the baseline. Renewable energy is the one that it's going up and down and up and down. And the good thing is on the load side, you can predict it with a pretty good accuracy because we have the data from the last 30 years. We know how much the consumption is increasing year over year. And we have very good models now. AI is playing a huge role that you can predict that, okay, on February 2nd, you could have the weather forecast and say, okay, 1 week from now, the temperature is going to drop. And from history, we know that the power is going to go up 10%. So you're going to ramp up production and put these 3, gas. And we have emergency gas power plants as well, just generators waiting idle, and they would just turn it on when something happens. The problem that we had in 2021 in the Texas power outage, the weather got so cold that the lines froze and you didn't have gas and the generators couldn't run. Some of them, we didn't winterize the wind turbines. We didn't winterize, mostly the gas froze, and we didn't winterize the generators. So the production, when they needed, and it got very cold, all of the people, turn on their, heaters. A lot of heaters are electric, gas dropped. And what happened was suddenly the production tanked. And to protect the grid, they had to do shutoffs, both an increase in production and decrease, it's going to damage the grid. And when a grid damages, so let me tell you something, if they didn't do planned cutoffs, it's going to damage the transformer in the grid. That would take some transformers, it takes 1 month to build, 2 months. Some takes 5-6 months to repair a station. And that would cause major blackouts for a few months if you want to repair the whole grid. But that's a great question. Yeah. So permanent magnet synchronous generators are used right now to reduce the costs and make it lighter. It's complete with the speed control with higher rating converter, capable of non-gearbox and or transmissions. And we have rare earth material usage in them, so they are more expensive, but on the other side, you don't use a bulky gearbox. So a concept quiz that we're going to have right now. I was using this as wanted to use this as attendance. Obviously, all of you are present right now. So in a wind turbine, the rule of power electronics is to transfer power from the generator that produces voltage at a variable amplitude and variable frequency to utility grid with voltage at a constant amplitude and constant frequency. Is this true or false? Yes, it's true, because we want, again, we have something that is variable and we wanted to have something that is constant and reliable, both frequency, and we could do it for voltage. Some utility applications, we have the transmission and distribution, HVDC transmission system, and the FACTS, which is flexible AC transmission systems. One example is for HVDC or high voltage DC transmission. this system is usually used if it's above 400 or 500 miles. And because of the large fixed cost necessary to convert AC to DC and then back to AC DC transmission, this is only practical in specialized applications. It's used for long distances over 400 miles or long underwater cables over 25 miles. It's providing an asynchronous means of joining different power systems as well. So if you want to connect Europe to US, obviously you don't want to do that. It can't do that. But if you want to connect two different power grids with different frequencies, one is 50, one is 60, one is like working on 200,000 volts, one is working on 400,000 volts. Its best way to connect them is to actually convert both to DC, couple them together, connect them, and then convert it back to AC. So what is FACTS or flexible AC transmission systems? We use them a lot in microgrids and smart grids. We have control of the voltages, we have control over the flow of power, and various devices like the SVC, STATCOM, TSC, CSC, and UPFC. You're going to learn this if you have the elective smart grids with me. I think that was now it's a upper level graduate class, but you will learn all about these and how we connect and control a smart grid. And all of that is through power electronics. So the goals of PE is the low losses and high efficiency, price of electric energy and cooling system. We want to actually be able to have precise control over them. Examples that I mentioned for the refrigerator and the HVAC systems right now, they are using inverters to be able to increase their efficiency and reduce your power bill. Competitive price, small size. They have become very cheap lately. Packaging density, integration of power and control components, and heat dissipation and energy efficiency. Obviously, you don't want to carry a large, bulky phone charger with you. We want to make it smaller and more efficient. So some requirements for power electronics is, one, it's their high efficiency, energy efficiency. Before I go through that, I want to finish these EVs. I'm going to jump and come back on the impact that these power electronics had on. I'm just going to give you one example of the impact the power electronics had on the technology, the transportation technology. So this is a picture of New York, Fifth Avenue in the 1900s. And there's a red circle. Do you know what the red circle is? Can you guess what the red circle shows? Okay, you can obviously tell from here. But all of these cars and all of these are actually running with horses. Can you see the horses and, Yeah, that's a car. All of them are running by, yeah, all of them are. And you would be surprised that the first internal combustion engine come out at 1880 something. The first electric vehicle come out in the 1820s, like 50, 60 years before we had internal combustion engines, we had EVs. And this is another picture from another era. And this is 1913. You would see that we have one EV and the rest of them are internal combustion. Yeah. Oh, that's a good question. This is how they charged it. This is the electric. Yeah, and it was back then, because internal combustion, you had to use this, you had to crank it by hand. A lot of people broke their arm using cranking it. It was dangerous to kill people. It was dirty, it was noisy. Electric EV was quiet, was cheap, easy to run, and mainly actually women used it because it was much easier to run. You didn't have to mess up with the crankshaft. It was difficult, and and this is obviously seeing a woman charging it. The range was limited around like 20 miles, but the thing is, in New York City there was a lot of charging stations. Now imagine this scenario, but then the oil and gas came, oil and gas industry, they saw they have a huge amount of byproducts, because initially when they use oil, they use it for, lighting and asphalt and so on. And there was a huge byproduct, and they saw, oh, they can use this. Actually, gas was a byproduct, diesel was a byproduct. Initially, they just threw it out. And then they used it as an internal combustion. There was an industry around that. Now imagine if EV took off and everywhere was EV. And in 2010, an engineer in Ford came, or I don't know, Elon Musk came and said, oh, I have a brilliant idea. Instead of having EVs, what if we put this combustible, this gas into the cars? And instead of having 100 parts in a motor, what if we build a car that has 2,000 parts, and you have to put oil in it, and you have to maintain it, change the oil, change the air filter, and someone would ask, oh, can you charge it at your home? No, you need build special these stations, and you go to those stations and you fill out your car, and it's gonna produce these nasty fumes, and it's gonna leak oil, and it's not very good at low end torque. It makes a lot of noise. And imagine how the first engines were. And everyone would probably say you're crazy, you're out of your mind. Why would you need a? But the history is all the other way around, because AVs are now much smoother. The only problem is we don't have enough, I could say, infrastructure for charging them. But if we had that, and the batteries and the amount of time and energy we spent on perfecting internal combustion from 100 years ago, obviously you can see that if it was spent on batteries, we would probably have batteries that will run 2,000-3,000 miles running. But it's how there's a huge industry behind the oil and gas and everything. And obviously that you can see that bullet train goes 500 miles per hour easily. I don't know if you've been in a bullet train. It's super quiet. You don't even realize you're in, going 200-300 miles an hour. And very quiet. So a car can't technically, with an EV electric motor, go that fast. And again, efficiency is around 93%. And the person will tell you, and if you ask them what is the efficiency of the motor, maximum is like 30%. That generates heat, makes it hot. You have to have a radiator, you have to have oil, you have to change air filters, you have to change your, if you put wrong fuel in it, it's going to destroy the motor, and so on. So this is evolution. And the power electronics, when it came along, from 1900 to 2017, obviously we didn't have a lot of progress until the 2010s, and suddenly we're back in the last 10 years, and you can see the huge progress that has been made. Then the charger wins from this, and it's interesting, to this actually. I don't know, have you seen one of the EVs? I think in the John Lennon garage. I would show you one of these after the classes. I'm just going to finish some of these. So this is 2017, again, New York City, Fifth Avenue, the same avenue. And you can see that we can now see again EVs popping up. They were absent for the past 100 years. Charging in 2017, now we have charging, which are actually wireless charging. Some cars, they are developing the technology, but obviously it's not very, very efficient. Let me go through. Yeah. And I'm just going to show you this small. And it's not John Lennon. Yeah, this is the EV. Huh. I forgot what was his name. Oh yeah, this is it.
Imagine being able to build an
Yeah. And if you look at it, it's so and this is the electric car. This is the EV from.
Yeah, you know, so the idea, I mean, it's such a beautifully put together motor. And although it looks like a carriage, it is a carriage, but it has some high-tech ideas for the time. You have leather fenders. See, leather was the carbon fiber in the day, very lightweight, very lightweight.
Sorry.
Well, these open and close. And you have to understand, this is even before the advent of the wind-up window. So what you had to do was you undo these here. These are, if you notice, they're like railroad time, you know, the self-start hadn't been invented yet. So steam was a hassle. Steam was dirty and messy and scary.
This is even before gas they invented. It was steam cars and these.
These are popular as women's shopping cars. So what they did was they really marketed them to women. They made it look like a woman's sitting room. You have the flowers. You see, see the clock and there's a makeup, you open up and there's face powder and, you know, makeup and all. But then the problem was, well, no man wants to buy a finished product. I mean, that was the problem. So consequently, electrics were relegated as women's shopping carts. But this thing went 100 miles in a charge. At the turn of the century, there were 15,000 of them in New York City. You could drive, there were charging stations all over the city.
Really? There were 15,000?
Oh, yeah, there were all over the place. There were a lot of them.
I mean, looking like this, looking like the phone.
Yeah, yeah, and they were really quite, you know, it's interesting, one day I was having my house, termite. They put the, you know, big tent over. So my wife said, oh, I stayed at Beverly Hills Hotel, we never stayed there. And I said, okay, so we'll spend 2 days at Beverly Hills. So I drive this to the Beverly Hills Hotel, and they go, hey, is that Mrs. So-and-so's car? I go, who's Mrs. So-and-so? She goes, oh, she used to come in and get her hair done every year for almost 50 years, and she would park.
In one of these?
I said, well, where? She goes, well, we haven't seen her in a year or two, and I tried, because she had just died, but she had a Baker Electric, and I never found the car. But from like 1935 until almost 2001, she would take this thing to Beverly Hills Hotel every week to get her hair done.
Well, go back to my classic car. Now, is it completely, it's slim, of course, I mean.
Yeah.
And does it have a transmission?
No, it's direct, that's the great thing about electricity, it's like steam, you have all your torque right away, yeah, so it'll climb any hill.
This is how they charged it, the charging station.
Edison batteries. Thomas Edison invented the alkaline battery to double the range.
And
of an
I
electric.
just want to show you how quiet and
Place your hand with it, and you turn your key.
There's some gauge, like bolts went up. And away we go. We'll go back to my classic car. The bills, I think the bills.
Yeah,
It just gets worse. With the price of admission.
Well, it just has that department store, menswear, lingerie.
now compare this to a Ford Model T. And
Once you can look down on another car.
You have that kind of superior feel up here.
And the nice thing is, you can look down on Prius owners with their gas polluting, 3-cylinder, whatever that is. Electric lines were a big deal in 1909. Most cars still had gas lines, so this was all electric. Like when I bought the E-Guys, my parking and leave the lights on.
okay, that's it for today. Thank you so much. And I will see you on next week. Oh, I just want to mention something. Just give me 1 second.